Good morning, all. Can you hear me? Hello, can you hear me?
Yes.
Okay. All right. So let us begin. I hope you all had a good break, but then the semester is upon us again. And so here we are. We're going to continue our series of lectures on recurrent neural networks. And I hope you remember what we covered last before the break. Can anybody remind me what was the last thing we covered? Anybody? RNNs? And what specifically about RNNs was the last thing we covered? LSTMs. Thank you. Right. So, but we're going to take a step back from there. The story so far was that recurrent structures can be are required to analyze time series, and they can be trained by minimizing the divergence between the sequence of outputs that they produce and the sequence of desired outputs through gradient descent and backpropagation. And I mentioned in the last class, or in the last week that we had classes, that the nature of this divergence can be a problem, right? So, but first, what kinds of recurrent networks can we have? Now, these figures, I've gotten these figures from Andre Karpathy. So here is a model: input, hidden layers, output layer. And here there is no recurrence. It's just a conventional MLP. The input feeds the hidden layers, which feeds the output. This is how we saw recurrent networks, that you have a series of inputs. They feed a hidden layer where the hidden layers get both the inputs and additional inputs from themselves at the previous time. And at each time, they generate an output. So you have a time synchrony between the inputs and outputs. Corresponding to each input, there is an output. But then you can also have other kinds. So this is the kind of thing that we do for, say, predicting the stock market, right? But then you can have other kinds of recurrence where you analyze an entire sequence of inputs and then finally make your prediction. So this could be, for example, if you are performing sentiment recognition in text, you have to read the entire sentence, and then at the end of the sentence, you have to decide whether this sentence carries a positive sentiment or a negative sentiment. Or you can have this kind of a structure. This is what we call an order synchronous but time asynchronous sequence to sequence model. So you have a sequence of inputs, you have a sequence of outputs, and the number of outputs is not the same as the number of inputs. The outputs are intermittent. Nonetheless, there is a correspondence between the input and the output. So, for example, if I had a speech signal and I was trying to recognize what was in it, my recognition might be a good day, right? But then if you look at this portion of the input might correspond to A. This portion of the input might correspond to good. And what follows here might correspond to day. So if you move these things around, these would have to move to in exactly the same way. So there's a correspondence, there's a strict correspondence between the input and the output, but it's not one-to-one. So where the outputs will be produced is not clear. It's because the outputs are intermittent. So this might be, for example, your A, this might be good, and this might be day. And so each of the outputs is going to be produced at the end of the event that it's recognizing. So it's order synchronous, but it's not time synchronous. Is this clear to you guys? What we're speaking of here?
I have
This
a
one.
question, sir.
Yes.
So basically, what you mean is that is it order synchronous because like the output sequence is in the same order as the input sequence, but it's not necessarily the same size as the input sequence, meaning like not only is there not one-to-one correspondence, but like so basically there's only like a output sequence for like a group of like for a group of like input thingies, and that group not and the
That's
number
right.
of input thingies that group is not given.
Yeah. I mean, they may, whether they are given or not is something that we will deal with in this lecture, but yeah. So the outputs are intermittent. Again, is this making sense to the rest of you guys? Yes, no, because we're going to focus on this. Okay, I have one yes, I'll take that. You can have other variants, the many-to-many variant, where you analyze an entire sequence, and once you've analyzed the entire input sequence, you generate a sequence of outputs. So this you might use this, for instance, when you're performing machine translation. You read the entire English and then generate the entire French. Or you can have a one-to-many, where you read a single input and generate an entire sequence of outputs. Can someone give me an example of where this model might be used? Anybody? What kind of problem would this be useful for? Anyone? I've helpfully put some, machine translation is the one on the left because the input is a sequence as well, right? And the output is a sequence. This would be captioning. You have a single image, you have to generate an entire text, right? So you see, they're all recurrent networks, but small changes in architecture can make them aptly different problems. So let's look at each of these first. This is your conventional MLP. It's for corresponding to each input, there's an output. There is no recurrence over here. Can we use this model to analyze time series? What do you think? Can we use this to analyze time series? Yes, no? What do you guys think? No? Only one timestamp. Only if there's param sharing. Okay, so I could, but this doesn't have recurrence. You have as many outputs as inputs, meaning the output at any time is unrelated to the output at the previous time. But if I'm actually looking at divergences between sequences, then the manner in which the recurrent nature of the problem is captured is through the divergence. There's nothing in the model that captures recurrence. But just by the fact that you're forcing the model to minimize the divergence between two sequences, you can hope that the model will capture something about the time series nature of the problem. But when we do this, we often make an additional assumption that even though we're analyzing, comparing two sequences, that we can actually compute individual divergences at each time instant, and then the divergences between the two sequences is just going to be the sum of the divergences at individual times, in which case, again, the recurrence breaks down. But this latter assumption is something that we often do simply because it simplifies the model in the math. It's if the divergence is bigger, what do you mean by bigger over here?
So if there's a greater divergence between the input sequence and like the output sequence, like does that imply that like the parameters we're using to like compute the output sequence, like the approximate output sequence, like they're not doing like a good enough job of capturing that like aspect to just said like the
We won't be able to
divergence.
we won't be able to attribute the error to any one factor. So we won't know whether it's because it's unable to capture the time aspect or whether it's just a lousy model, right? So that's something you can never really be sure about.
Oh, so the divergence, like it's sort of like a proxy for like how well you're capturing the time aspect, but it's not absolute.
Yeah, that's right, right? And so when I use as an MLP as to model time series, but I continue to assume that the divergence between the two series is the sum of the divergences at individual times, then it simplifies the problem because the global divergence is simply the sum of local divergences. But in doing so, I lose the time series nature of the data. But this is an assumption that we will often make in other settings as well. So here is your first poll. And let's see if that made any sense to you guys. Can you guys see the poll? Okay, I'll give you 5 seconds, guys. All right, let me end the poll. Here's what you thought. Let me stop sharing and go back. So what is the answer to the first question? True or false? True. The second one, true or false? Also true, right? Conventional MLPs can be used to model sequences, although they have no recurrence. Here, the sequence nature of the problem is captured through the divergence. So that's easy. Now let's look at this other one. This is the many-to-many time synchronous model, where corresponding to each input, there's an output. So here, the network would produce one output for each input, and it can be used in many problems, like the stock market, where you're making predictions every day, or part of speech tagging for English sentences, where every word has a corresponding part of speech tag. So there's a one-to-one correspondence. And the recurrence may be strictly left to right or bidirectional. It doesn't really matter. So if you have a one-sided network, you'd be processing the input left to right to produce an output after each input. If you have a bidirectional network, you'd be analyzing the input both left to right and right to left. But the key thing is that corresponding to each input, there is an output. And so this time synchrony between the inputs and outputs is what is key. Now, in my slides, I'm going to assume, just for illustration, that we have a one-sided model, but you can just change that to a two-sided model without changing any of the rest of the lecture. Now, in this setting, once again, there's recurrence in the model, and again, the recurrent model generates a sequence of outputs, a time series. We have a desired time series output, and the divergence is the divergence between the desired output sequence and the actual output sequence. And this divergence is what we want to minimize. But then again, the first step of training required that we be able to compute the derivative of the divergence with respect to every one of the outputs of the network. So being able to compute the derivative of the divergence with respect to any of the yt's is key for backpropagation to work. And being able to compute this divergence means we need to be very clear about how the divergence is defined. It must be defined in a manner that this derivative is computable, right? So once again, there's a very common assumption that we will make. When a one-to-one correspondence with the actual output. In which case, you can assume that the total divergence is the sum of the divergences at the individual times, and then the derivative of the global divergence with respect to any input is simply going to be the derivative of the local divergence at that time. So, this making sense? Yes or no? Okay. But for this, here is the key thing. You need to have a one-to-one correspondence between the desired output and the actual output. And in many problems, you won't actually have this kind of a one-to-one correspondence. So what you will find, both in this class and the next few classes, and in general in many problems where we use recurrent structures, is that we somehow manipulate the desired output and the problem setting itself to squeeze a one-to-one correspondence between the desired and actual outputs, so that we can define our divergence in this manner, and so that we can compute the derivative of the divergence with respect to the individual outputs. So this is not a natural form of the problem, but somehow we're going to manipulate the problem so that this becomes possible. And so that's what we will do. So here is our second poll. All right, 10 seconds, guys. Okay, let me end the poll here. Here's what you guys thought. Let me stop sharing that. Okay, first statement, true or false for time synchronous RNNs. Second statement, true or false? False, right? The third one, true or false? True. Right, so the first and third are true. Beautiful. So now we've seen two problems, but now let's go to a third problem. This one, where you analyze an entire sequence and generate an output at the end. Like when you're doing sentiment classification, or since I'll be using speech as my primary example over here, if you were doing phoneme recognition. So here what you would do is, or if you're doing question answering where you just have to, the question answering is a multiple choice, set as a multiple choice task, then your question would come in, color of sky. And until you see the word sky, you can't really answer it. So the only time you can answer is after you see the word sky, at which time you can pop out the word blue, right? So there's a sequence, the input is a sequence, there's an output, it happens only at the end. Or if I'm doing phoneme recognition, I'm going to see the entire sequence of feature vectors from the speech. And once I've seen the last one, that's when I can decide what the phoneme. Okay. The actual output is going to be the probabilities. Wait, can you hear me? Yes, no? Okay, sorry. I
Now,
have some
yes.
minor, yeah, I'm having some internet hiccups today, and I'm hoping this class goes through. But anyways, so what the actual output of the network is going to be a set of probabilities, one for every class, right? And when you want to perform classification, you're going to pick the class which had the highest probability, right? So this is what we actually do. This is some you would have an input sequence. The entire input sequence is analyzed. And then at the end of the input sequence, you get a probabilities for all classes. It would be a probability distribution, would be over the phonemes, and you're going to pick the phoneme with the highest probability. But again, remember that every column is identical to every other column, right? So what happens over here and here? Do we not have outputs over here, or does something happen here? What do you guys think? What happens at these locations? We don't consider them, right? You actually have outputs at each location. We just ignore them and just read the output at only the final output, right? Because when you're performing inference, you have to wait for this guy to decide what happened. But that kicks in when you're performing training. So when you're training, again, you're going to be given input-output pairs. The input would be a sequence. There would be an output probability distribution. You have a target output. You would compute the divergence between the two, and you'd backpropagate those divergences to the model at each time. But in doing this, I'm missing something important. What am I missing? Am I making full use of my data and my model, or am I losing something over here? What do you guys think? Anybody? Divergence? Any other answers? Okay. Is the model producing no outputs at all over here? Or am I ignoring it? We're ignoring these guys, right? So does it make sense to ignore them? Or can I use them? What do you think? I should be able to use these, right? And so here's what I can do. I can say, the shortcoming is that you're pretending there's no useful information over here. But the fact is, output is being produced there. And so if this is the phoneme R, if it was R out here, it was probably R out here as well and out here as well, right? And these guys get partial information, at least partial information about what the final out have at least partial information about what the final output must be. So here's a simple trick we can do. I can say that the target output at each of these times is the same. And in doing this, now I've converted this to a familiar problem. There's a time synchronous output, desired output corresponding to each input. And there's a time synchronous actual output at each time. And so then I can now define my overall divergence as the weighted sum of the divergences at the individual times. And you're back in familiar territory. This making sense to everybody? Yes, no? Right. So why do I have weights? Why do I have weights? Anyone? Losses? No, there's some settings where it doesn't make sense to use these guys. If I'm looking at a question answering, there's no reason for me to believe that the answer here and here must be blue, right? And so it really depends on the problem setting. So this is just a generic generalization because the full information might not be there yet. But I'm going to continue assuming that the full information is present, okay? So this, exactly. So this has been dealt with. Now let's go to this problem. This is the one that's most interesting for today's class. Here the output is order synchronous, but time asynchronous, meaning the output has an order correspondence with the input, but it doesn't. But the number of outputs are maybe fewer than the inputs, so the outputs are intermittent. And this, for example, would happen when you're doing speech recognition. You have a sequence of vectors coming in, and only when the sequence of vectors corresponding to any particular sound has completed are you going to output that sound. So maybe all of these vectors correspond to B. And so when you get to the end of B, you're going to output a B. When you get to the end of A, you're going to output an A. When you get to the end of T, you're going to output a T, and so this is the word but, right? So this guy, as you can see, can you see that this is basically just a simple extension of this model? Can you see this here? Right, I've just concatenated many of these guys, but the simple extension makes things really, really horrible. And this has to do with the fact that the model actually outputs something at every time. We are supposed to read the outputs only at some times, but we don't know when to read the outputs. And this is the source of the primary source of the complication. This clear? Right? And so that's what we're going to have to deal with. Now, once again, how can we come up with some solutions for figuring out when to read the output? How about we don't decide? So remember again that the network is generating a full set of probabilities at each time. So in single time. And so instead of trying to decide when you must read, you could just read the most likely thing at each time. Again, remember that any neural network with a softmax or logistic output is actually outputting an estimate of the a posteriori probabilities of the classes given the output. So what these guys are basically the a posteriori probabilities of the classes. It's the probability, each element is the probability of one class given the output. And so when you pick the element with for which the output is the largest, you're actually picking the most probable class. That is the act of performing maximum a posteriori probability classification. And this is what you do in a simple NLP. We're going to use, we can use the same thing over here. So what we really want to do, again, when I'm trying to recognize the word, say, that was spoken, I want to find the phoneme sequence which is most probable given the input. And observe that this phoneme sequence may not be as long as the input itself. This could be, for instance, 70 vectors. This could be just 3 phonemes, right? So we don't know the number of phonemes over here, but we are trying to pick the phoneme sequence or the symbol sequence in general that is most probable given the input. So is this MAP, maximum a posteriori classification rule, making sense to you guys? This one here. Yes or no? Okay, so this is what we want to do. And how can I do this? I'm going to ignore the fact that the length of this is not really known and can be shorter than the input, or can be shorter than the output. I just go ahead, keeping in mind the fact that I get a full set of probabilities at each time. I can just pick the most probable symbol at each time. Again, remember that the number of output symbols is most likely smaller than the actual input length. So what can I do? I can just merge subsequent outputs if they're identical. So both of these are G. So I can merge this and say the G really must be output over here. All 4 of these are F. So I can merge these and say the F really must be output over here, and so on. So if I did this, is this making sense? And second, is there a problem with this? So is this making sense, guys, first? What we're doing here. Okay, and what is the problem? Somebody give me a second yes. What is the problem? How is length? The length you have, I'm getting one output for each. And when I'm merging it, I'm eventually getting intermittent outputs, right? If you have repeated stuff, how do I know whether I should be grouping them like this or like this? There's no way of distinguishing between repetitions. So you can't distinguish between an extended symbol and repetitions of the symbol. And also, this thing might make no sense at all, right? So what are the possible remedies? One, you can impose external constraints on what sequences are allowed. This is what you would be doing if you were working at Google, for instance, that you have an external dictionary, some other knowledge base or database which says here are the valid. Or you can use a special separating symbol to separate repetitions. We're going to look at especially the second one, with a popular solution, but later in the class. For now, I'm going to assume that we have some idea of how to perform inference that will give us intermittent outputs. This business of performing inference is what I will call decoding. And we will go on. So is this making sense so far? Everything we've covered so far? Yes? Okay. Now, again, remember that I'm actually picking one symbol at each time and compressing them. So eventually over here, I might end up with, bead, right? But this is not necessarily, bead is not necessarily the most probable order synchronous output. Bead is just the most probable time synchronous output. because I've picked the time synchronous output sequence that was most probable, and that gave me an order synchronous sequence. But the reality is that there are other ways of generating this order synchronous sequence, beat, which I have not considered. So this is actually a suboptimal decoder, which finds the most likely time synchronous output sequence, which is not likely necessarily the most likely order aligned sequence. Now, if that didn't make sense to you, it will begin making sense to you in the next class. But just a heads up, right? But for now, we're going to assume that this business of inference is partially addressed. We're going to return to it in the next class. How do we know when to output symbols? The fact is the network produces outputs at every time. Which of these must we read? We have seen one solution to this. Here's the bigger problem that we are interested in for now, for the rest of this class. How do you train these models? Now, again, training, you're going to be getting, each training instance is going to be an input sequence and a corresponding output sequence. So you might get, for example, a recording, and you might be informed that this recording is the word but. So the recording is here, in this example, is 10 vectors long. The output has only 3 symbols. And just for convenience sake, let's assume that whoever gave you this training data also told you that B must be output at time 2, must be output at time 6, and T must be output at time 9, right? So it's not only giving you the output symbols, but also the location at which the output must be generated. If I were given this information, then how could I perform training? Very simple. But before we get to this, I have a name for this information. The information that tells me that B must be output at time 2, must be output at time 6, and T must be output at time 9. I'm going to call this the alignment. It's the alignment of the output to the input. The output is 3 symbols long. The input is 9 vectors long. And the correspondence of the output symbols to the inputs is how the output is aligned to the input. So the B is aligned to 2. Is aligned to 6. And T is aligned to 9. So is the notion of an alignment coming across to you guys? Yeah, and so this is the alignment. The timestamps of the output symbols tell us how the symbols are aligned to the input. And the same symbol sequence may be aligned to the input in different ways. So here, for example, if B is output at time 3, it means these first 4 vectors all correspond to B. If A is aligned to time 7, it means the next 4 all correspond. Aligning the same output symbol sequence to the input. And so they can have given symbol sequence can have many different alignments to the input. Simply knowing that this is the word but doesn't tell you the alignment. The alignment is extra information that we are assuming when I say that I know the exact times at which the output must be generated. Is that coming across? Is that clear? Yes. Okay. And so if I have alignment, then how do I train? The training data is going to be the input sequence plus the output sequence. You're also given the alignment. You're told where each symbol is being output. And so in the forward pass, you just pass the data through the recurrent network, and you know the times at which the output must be read. So you could read the output at time 2, at time 6, and time 9, and compare those to your target output. And so the total divergence is going to be the sum of these 3 outputs. And it's the derivatives of that divergence that you're going to back propagate, right? So this clear? Yes. I'm missing something here. What am I missing? What would I be missing out here? Weighted divergence. The other outputs, right? These guys are being ignored. And so I know that the network actually produced outputs at each time. And if this entire region corresponds to Burr, then this should likely also assign high probability to Burr. So should this. And so also if this entire region corresponds to each of these three must assign high probabilities to This is what we require if the model were doing things right. And so instead of just computing the divergences at the specific output times, we can replicate the output symbol at each time through the duration of that symbol, and then compute the divergence at each time. So in doing this, we've converted what was a somewhat odd problem to something familiar. And what is the familiar thing we converted this to? We now have an output sequence which has a one-to-one correspondence with each actual output of the network. And once you do this, then I can compute divergences locally, and then I can sum them up, and that's going to give me my overall divergence. Yeah, Shiva. So this making sense to everybody? Yeah. And furthermore, here's the thing. If this is the phoneme t, and I compute the divergence over here, and I compute the Kullback-Leibler divergence or the cross entropy loss, what did we know from the previous classes? The cross entropy loss is simply the negative of the log of the probability assigned by the network to the target symbol. And so this becomes even simpler. It's the sum over time of, or minus the sum over the time, over time, of the log of the probabilities assigned by the network to the target symbols at each time. Remember this formula. So is this formula making sense here? This one here, guys, because we will see this today and again in the next class. Yes, okay. Basically, I have smeared the target output over all the over the entire input. So now I've made the target output time synchronous, which means there's a target output at each time, and the actual loss is the negative of the sum over all times of the log probability assigned to the target symbol at each time. We're not considering a weighted average. We're going to assume that all weights are 1 because I mean, you could consider a weighted average, but where those weights come from become a bit of a challenge. So here I'm going to ignore that. Okay. So any questions? Could it be that x0 and x2 output b and x1? Yes, it could. But then again, this x1 corresponds to b. So if x1 outputs something other than b, then is the model doing a good job? Daniela, would you say the model is doing a good job if it just decides that this is n?
Is it supposed to
What do you
represent
think?
like somebody saying B continuously, so it shouldn't?
It shouldn't, right? So the model could do this, in which case it means the model must be updated, right?
Okay.
Yeah. So, Ron, it could, but that's slightly beyond the scope of what we're covering today, okay? Now, here's the problem. We're assuming here that the alignment has been given, right? In real life, nobody's going to give you the alignment. They're just going to say, here's a recording. This is a recording of the word but. And so only the sequence of output symbols is provided. You're not going to be informed where the output actually occurs. In this case, how do you compute the divergence? And how do we compute its gradient with respect to the outputs? Clearly, you can see immediately why I said that the fact that you're looking at the divergence between two sequences is a challenge. Here's a situation where you have a target output, you have an actual output, and somehow you must compute a divergence, and it's not even clear how you would do this. And this is where ingenuity comes in, right? So do you see the problem here? And this is what you're going to get in many problems. So let's see how we deal with this. We know how to train if the alignment is provided, but the alignment is not provided, right? So what are possible solutions? Let me pick your mind, pick your brains. If this alignment has not been provided, what are the possible solutions? Can you suggest something? Any ideas? Consider all possible ones. Guess, right? That's what, Irene, beautiful, right? So what I can do is guess the alignment, or as Ritvik says, I can consider all possible alignments. These are the two options, right? So we're going to look at the first option today. How we would do this if we guess the alignment. So here, if you're told, for example, I keep flipping my examples. So here my word is now beefy. I don't know why. It's been on my slides forever, so that's what we'll continue with. If I have, that's right, okay. So if I have been informed that this input corresponds to the word beefy, then I'm going to somehow assume that, come up with an initial guess and say, you know what? I think this is the, I think this is E. I think this is fur, and I think this is E again, right? And there are different heuristics you could use to come up with this initial alignment. You could say, for example, I'm going to split it uniformly between the output symbols, or I know something, vowels are longer than consonants, so I'm going to make B shorter than E. It doesn't matter. The point is you use some heuristic to come up with an initial alignment. And once I have an initial alignment, then I can just use the strategy that we're already familiar with, which is to say that I can compute the time step-wise divergences and train the model for this alignment. But now that I've trained the model for this alignment, the expectation is that this alignment is obviously not going to be correct. It's a guess, right? But the expectation is that you've not, you've generally not been completely wrong, and that you're more right than you're wrong. And so if you use this new model that you've learned to go back and re-estimate the alignment, the new alignments will be better than what you began with. And you can prove this mathematically, but yeah, they're not going to be worse in any case in a probabilistic sense. So up the new alignment, and then I can use the new alignment to go back and retrain the network using the updated alignment. And then once I retrain the network using the updated alignment, I can go back and use the retrain model to go back and realign my inputs again, and keep repeating this process where I iteratively train the network and re-estimate the alignment for each training instance. This is making sense, this one here, this loop. Yes, no? Yeah, okay. And so that's what we're going to do, right? So this requires, okay, guessing the first alignment is easy. You come up with some heuristic and you guessed your first alignment. You trained your model. The real challenge is this guy, retraining the alignment for each training instance using the model that you just learned. How do we do this? Again, let's go back and look at the alignment again. What is the alignment? The alignment tells us which portion of the input corresponds to what symbol in the target sequence. So here in this alignment, it tells me that this portion of the input corresponds to B, this corresponds to and this corresponds to T. Or here, this corresponds to B, this corresponds to and this corresponds to T, and so on, right? So any given input can have many different alignments. And if I have the alignment, I can characterize the alignment by saying, you know what? This entire region is B. This entire region is A. This entire region is T. And so in doing this, I've basically expanded my original symbol sequence by repeating them, repeating the symbols so that now I have a one-to-one correspondence between the expanded sequence and the inputs. And once again, there are many different ways of aligning a given input, a given target output to an input, which means I can have many different such expanded sequences corresponding to the input. So this making sense? Yes, no? Okay. And so here's where we are, right? I'm going to call this original sequence a compressed sequence. It's compressed because more often than not, it's going to be shorter than the input. And I'm going to call this one where I've aligned each symbol against the input and converted it to a time synchronous sequence through repetition. I'm going to call this an expanded sequence or an aligned sequence. I can also call this just an alignment, right? And so corresponding to any compressed sequence, there can be many different alignments. And so also many different alignments, where an alignment is basically a time synchronous symbol sequence, can be compressed to the same compressed sequence. So again, to clarify, a single compressed sequence can have many different alignments. By alignment, I'm really speaking of a time synchronous symbol sequence where I have one symbol per input. And many alignments can in turn be compressed to the same compressed sequence. And so the problem of finding an alignment for a compressed sequence is to see which of these is best aligns this guy to the input. So we want to find the best expansion of a compressed sequence for a given input given a model. The information for how best to align this guy to the input is going to be obtained from the model. This clear? Yes, no? Okay. So here it is, right? The alignment problem. You're given an unaligned k-length compressed sequence like beefy, and you have an n-length input where n is typically greater than k. It can't be short less than k. You're given a trained network, a recurrent network, and we want to find the alignment that best explains the compressed symbol sequence. So you're given the compressed symbol sequence. You're also given the input. You want to find the alignment, meaning the time synchronous symbol sequence that best or explains this compressed sequence, or in probabilistic terms, you want to find the most probable alignment that compresses to this compressed sequence. This clear? Yes, okay, all right. So let's see. Actually, there's a poll here. Let's see. Okay, 10 seconds, guys. Right. Let me end the poll. Here's what you guys thought. Stop sharing. Okay, let's ask your opinion. First statement, an order synchronous symbol sequence that's shorter than the input can be aligned, true or false? True, right? The alignment is a time synchronous sequence, true or false? True. The third one, the symbol sequence that's time synchronous with an input can be compressed to a shorter order synchronous, true or false? Okay. What about the fourth one? Order synchronous symbol sequences that are shorter are compressed symbol sequences. True, right? And the last one? There's ones. Okay, you pretty much
Prof,
everybody got it, right? Beautiful. Yes.
there was an issue with my computer. Could you like quickly open the poll again, or?
I just lost
No,
you.
no, there was an issue with my computer. Could you like open the poll again, sir?
Wait. Have I lost you guys?
Mm,
Can you guys hear me? Okay, fine.
I can hear you now.
I couldn't hear. Okay, can you repeat the question, please? Yeah. Can you
Oh,
repeat the
sorry.
question?
There was an issue with my computer. Like, could you like open the poll again? Because I've been like listening, but like there was just a quick issue with my computer. Like, it's all right if you can't.
So what did you miss?
I missed filling out the poll because my computer like froze for a minute. I don't think it was an issue on your end. It was an issue on my end because of my computer.
Well, no, so since I'm not sure exactly what you missed, let me continue, right? We'll run out of time. At the end of the class, I can go over some things with you, okay? So let's continue. So now, here's the thing. Here's the problem again. Corresponding to any compressed sequence, there are many possible alignments. And we want to pick the alignment that's most probable for that compressed sequence. So let's see how we can do this. Again, remember that at each time, the network outputs probabilities for every symbol in its vocabulary. So you can see the outputs of the network as a table where the columns represent time and the rows represent symbols. So each row represents the probabilities assigned to a single symbol by the network across time. Now, in our example, let's say I have a target training, a training instance where the target output is the word beefy, right? B-E for E, right? So I want to align beefy to this input. Now, if I just pick the most probable symbol at each time, would this be an alignment of beefy to the input? Yes or no? If I just simply pick the most probable symbol, would this be an alignment? Why not? So why not? Anyone? So the symbols over here, that the most probable symbol may not even be in beefy, right? It could choose the wrong symbols. So can you suggest a solution to this? How do you prevent it from choosing wrong symbols? How would you prevent it? Mask it. Okay, so let me mask everything out, everything but the wrong symbols. So now I'm only left with the rows of the probability table corresponding to the target symbols. And I can think of it differently. I can say that from the original probability table generated by the network, I pick out the rows corresponding to the symbols that are in my target output, beefy, and only look at this reduced table. Now, this guarantees that I'm not going to output unnecessary symbols. And so I'm only going to perform my alignment on this reduced grid because we are assured that only appropriate symbols will be hypothesized. But if I go ahead and just pick the most likely symbol at each time, is this going to be an alignment of the word beefy? Yes or no? What do you think? Why not? Why not again? Out of order, right? Look at this. This is B, phi. This is just not, the order of symbols is not enforced. So we need to enforce the order in the symbols. How can we do that? Anyone? How would you enforce the order? So time varying masking. Here's a simple trick. This is my target symbol sequence, B, phi, right? So I'm going to make a reduced table, but instead of just using, just looking at only the rows corresponding to my target symbols. I'm going to arrange them in order. And then corresponding to each symbol, I'm going to pull out the row corresponding to each symbol and place them in the table over here in the same order as my symbol sequence. So the first row is the row of probabilities for B. The second row is the row of probabilities for E. The third is the row of probabilities for F. And the fourth is the row of probabilities for E again. Now observe over here that E occurs twice in my target sequence. So I've actually pulled that row out twice. In this reduced table, I am seeing the same row twice. Is this construction clear to you guys? Yes or no? Okay, very simple, right? And so why do I bother with this construction? It's very simple. It turns out that if I think of this row as a table, then or if I think of this collection of rows, arrangement of rows as a table, and I decide to walk a path from the top left cell of the table to the bottom right, and I follow two simple rules. At any point, I can either go right or I can take one step diagonally downwards. And second rule is I must always begin in the top left corner and end at the bottom right corner. Then what kind of paths would I have? I'm going to get a series of bursts. Then because I'm taking one step down, I'm going to have a series of E's. Then because I'm taking one step down and diagonally across, I'm going to get a series of F's. And then I'm going to get a series of E's. What is this? This a path. So I'm not blocking anything, Sumi. I'm literally just copying those guys over. Beefy was my target sequence. This was my training sequence, right? So I just pulled out the B from here, the E from here, the F from here, and E again. And so I've constructed a new table. I'm not blocking anything. I've just constructed a new table. That makes sense, Sumit? Okay, and so if I have paths of this kind, the sequence of cells that the path visits, what is it? What is the characteristic of the sequence of cells? This is going to be a chunked monotonic path that follows the output symbols, right? This is a valid alignment of the symbol sequence to the input, is it not? It says that B is the first time instance, E is the next two, F is the next three, E is the next two, right? So do you see how this path represents an alignment of the input to the symbol sequence? What about the rest of you? So can you see that? Yes or no? Right, okay. And so now this guarantees that the sequence this is an expansion, it's an alignment of the symbol sequence, and I want to find the most likely such alignment, right? Now, in order to find the most likely such alignment, I need to set up a mechanism whereby I can compute probabilities for each of these alignments. So here's what I'll do. I'll convert this table to a graph by just saying I'm going to have horizontal rows, horizontal edges, and diagonal edges which go from each cell one step down, like so. And so any path, so B is a source, E is a sink. Any path through this graph from source to sink represents an alignment. Can you see that? Yes or no? Okay. Furthermore, I'm going to say that each of these edges has a score of 1. And each of these cells, of course, is a node, and it contains a probability. So this here contains the probability assigned to the symbol B at time 0 by the network. This one, for instance, contains the probability assigned to symbol F at time 5 by the network. So every one of the cells has a probability assigned to a symbol by the network at a time, right? And so I want to find, so when I pick any path, if I just multiply the sequence of probabilities of all the nodes in the path, I'm going to get the probability of the path itself. And I want to find the most probable path. So here, for example, if I look at this subpath, it's BER followed by BER followed by E followed by E followed by FER. The probability of this path is going to be the probability of BER at time 0 times the probability assigned to BER at time 1 times the probability of E at 2 times the probability of E at 3 times the probability of FER at 4. So it's just this product of the probabilities of the nodes on the path at each time. So is this making sense? Yes, no? Yes, okay. Now, how many paths? So I want to find the path from the beginning to the end, which has the highest overall probability. That's going to give me the most probable alignment of B phi to the input. But how many paths do I have in this graph? Over here, overall. Anybody? How many paths do I have? So it's going to be this, very simple. Let's say at this time, I have a total number of subpaths, which is say L, right? Now, each of those paths corresponds to a node which has 2 children. So by the time I get here, it's going to be 2L. Those 2L, each of those paths has the terminal node in each of those paths has 2 children. So there's going to be 2 again. So it's going to be 2 raised to n, where n is the length of the input. And so even in the simple graph, you have an exponential number of paths to search through. And so we're going to have to search. If you want to find the most likely path, you're going to have to search through this exponential number of paths and find the path with the highest probability. So do you see the challenge here, guys? Yes, no? Right. And so how do you solve it? You're all computer science. Most of you are computer science students. How would you solve this? Anyone? Lots and lots of graph search algorithms, right? And what would be the simplest solution over here? Anyone? Greedy search? No. You want the optimal one, right? So what would be the best? What are the kinds of search that you've encountered in your courses on graph theory? Dijkstra, depth first search. What would be the most efficient over here with a fixed time? Breadth first search, right? BFS. Thank you. That's what we're going to do. We're going to use BFS. Okay. For those of you who don't know what we are talking about, here's what we do. We're going to try to find the most probable path from source to sink. You can do this using any dynamic programming algorithm. We're going to look at the Viterbi algorithm, which is a breadth first search algorithm. So here's the basic idea behind this. Let's try to consider the best path from the source to say this node. This node has only 2 parents, this one and this one. So let's say the best path to this parent had a score of 7, and the best path to this parent had a score of 8. So either this guy could be extended here or this guy could be extended here. Which of the 2 would you choose to extend it to this term here? The one that ended here with score 7 or the one that ended here with score 8? Which would you choose? The 8, right? Because this is going to give you the highest overall score. It's very obvious. And so that's the basic idea. The best path to any node must be an extension of the best path to one of its parent nodes. And the best parent is simply the parent with the best scoring best path. So each parent has a best path which has a score. And so I choose the parent for which the best path score is highest and then just pick that. It sounds complex when I say it in words, but when I give you an example, it's obvious. So for example, if the best path score to this guy had a score of 7, and the best path score to this guy had a score of 8, then just by inspecting it, you know that the best path to this one must come from here. And the score of the best path that comes here is going to be 8 multiplied by this node probability. That making sense to everybody? Yes, no? Okay, and so that's the basic idea here. That's all we will do. we are going to find the best path to each node, where the best path to each node is basically is the path through the best parent extended to the current node, and correspondingly, and how do you choose the best path? You're going to choose the best path based on the score. And then correspondingly, once you've found the path, you can compute the score to the node itself. So let's actually see this algorithmically, so it'll be clear. And so here's what we're going to do. We're going to dynamically track the best path and the score of the best path from the source node to every node in the graph. At each node, you're going to keep track of who the best parent was and what the best path score to the node was, which is obtained by simply multiplying the best score of the best parent with the node score. And once you do this, you're going to find best path scores from this node to every node in the graph. So then you'd find the best path score to this guy, but you'd also find the best parent, and then you just track your way back to find the overall alignment. So, and so here, or at least with some visualization, some notation. Here I have 4 symbols. The first symbol is B, the second is E, the third is F, the fourth is E. I'm just using the shorthand. I'm saying S of R is the symbol in the rth row. So S0 is going to be B. S1 is going to be E. S2 is going to be F, and S3 is going to be E again, right? So is this notation clear, what SR means? Yes, no? Okay. And within each node, this term represents the probability assigned to the symbol in that row at the time given by the subscript. Okay? So Y superscript SR subscript T is the probability assigned to the symbol in the rth row at time T by the network. Again, remember that this has actually been read from a longer probability table at time T. So you just read this guy has been read off from here, maybe this guy and this guy have maybe been read off from here, and this guy has probably been read off from here. I want you to remember that these didn't just magically appear, they've been actually pulled out from the larger probability table. And so having done that, now let's see how this goes. I'm going to go through this one step at a time, okay? So let's look at the very first column. At the very first column, none of these nodes have any parent because they're the first column. So their best parent is just a null, okay? Now, these nodes are not allowed to be the first node in any path. So the best path score to these nodes is simply going to be 0. They are disallowed. They have a best path score of 0. That making sense? Yes, no? And this is a path that is one long, and the best path score is simply going to be the node score itself. Y superscript S00, which is YB0. Is this making sense? Yes, no? Okay. And then having dealt with the first column, let's go to the second column. In the second column, this node, how many parents can it have? How many parents can this one have? Just one. So the best parent is simply going to be, I just need to keep track of the row index. The best parent is 0. And the best path score to this guy is going to be the score over here times the score of this node, which is best score at t-1 0 times the probability of this node itself, right? And then that's a special case. Now this guy, how many parents can this have? How many parents can this one have? Anybody? It can have 2. It has paths from both guys. It's just that this parent has a path of a score of 0, right? There's only one best parent simply because this has a score of 0. That making sense? And so you're going to keep track. This was my best parent. You don't even need to write special cases, right? And the node score for this guy is the score of the best parent times the node score over here. Now, if I go to the next two, each of these guys can have two best parents, but all parents are equally poor. So it doesn't matter what you get in the node score. So overall, because you're multiplying zeros with something, these guys are going to get a 0 score as well. And so you've gone down this column. Now you go to the next column. This guy again has only one possible parent. So the best parent is simply going to be this node over here, which is to say row 0. The best parent is row 0, right? You keep track of this, who the best parent was, and then you compute the best path score to this one as the best path score for this one, which has already been computed, multiplied by the node score over here. And then for the subsequent guys over here, these guys, each of them has two possible parents. And you're always going to, so although I've not shown the line over here, there's actually a line here, right? And for each of them, you're going to pick the parent which had the highest best path score, which was computed when you went down the previous column. And you're going to keep track of it like so. And then you'd multiply the best path score of the best parent with the score of the node itself to obtain the best path score to the node. This making sense? Yes. No? And so you can do this down this column, right? And this unfortunate guy, it doesn't matter which parent he chooses, he's going to get a score of 0. So, and then you go down this column and do the same thing. You go down to each node, and of all the parents, you pick the best parent, and you store a pointer saying, indicating who the best parent was, and then multiply the best path score of the best parent with the node score itself to get the best path score for the node. And you can keep doing this forward until column-wise, you have filled in the entire table. What is the total number of computations over here? It's going to be the size of the table times 2 because each node has only 2 parents. And so that's going to be polynomial. It's not going to be exponential, right? This making sense to everybody so far? Okay. And once you've done this, you know that the final node in any alignment must be this guy. So you can just ignore all of these guys. So you already have the best parent of this one. And the best parent was part of the best path, right? So you know the final node in the alignment must be this. You can track its best parent and 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 its best parent all the way down back to the beginning of time. And in the process, you're going to get the most likely alignment because you found the process found the most likely path from here to here, one step at a time. And so this is going to give you the most likely overall alignment of this compressed sequence to the input. That makes sense? Yes or no? Okay, very easy, right? And so here is your, we call this Viterbi decoding for historic reasons. Can you see the poll? Okay. 15 seconds. All right, let me end the poll. Here's what you guys thought. First statement, true or false? Second one, true or false? The third one, true or false? False, right? So, okay, everybody's on. I have some pseudocode over here. I'm going to skip the pseudocode. But what we got at the end of it was an alignment of the compressed symbol sequence to the input. And now we're going to treat this alignment as ground truth, which means that now you have a one-to-one correspondence between the target, which is obtained from this alignment, and the actual outputs of the network. And so now you can compute a divergence by just comparing these guys, and you can compute the derivative of the divergence with respect to each of the outputs. So the divergence is going to be the sum of the KL divergences at each time. But then again, at each time there's a single symbol, right? So we know that the KL divergence between a symbol and the output of the network is simply the negative of the log of the probability assigned to the symbol by the network. So the overall divergence is going to be minus of the summation over all time, the log of the probability assigned to the symbol on the best path at time t. And again, we've seen this before, except now this is a guessed alignment. And here's the key thing. If I want to compute the derivative of this divergence with respect to the output of the network, remember, the network outputs probabilities for many symbols, every symbol in the vocabulary, right? So given that it generates outputs for every symbol in the vocabulary, let's say this target symbol that you found on the best path was this guy. Then what is that's the only one that features in the loss, right? So what is the derivative of the divergence with respect to this term? What would it be? This term that doesn't actually feature in the output, in the loss. It's going to be 0. And so the derivative of the divergence is going to be 0 for everything except the symbol on the aligned sequence at time t. And for that symbol, because you have a minus here, the derivative is going to be minus 1 over the probability assigned to the symbol. And you can see again that a negative derivative means you're asking the network to increase. Why? So gradient descent is going to say that if you want to go in the direction of steepest descent, you want to increase the probability, right? So far so good. And so here's what we're going to do. We're going to initialize your alignments. Then you're going to use the procedure that we just saw to get alignments, new alignment. You're going to train a model with the alignments. Then you're going to use the procedure that we just saw to obtain updated alignments for all of your training instances. And then use the updated alignments to go back and retrain your model. And you keep doing this till things stop changing. And what I mean by things stopping changing is that the probabilities of the most likely alignments will no longer increase. This procedure is guaranteed to keep increasing the probability of your alignments, if in batch mode at least, with each iteration. And at some point, it will stop increasing. So there are a couple of different ways of doing this. You can go through your entire training data and determine alignments for every training instance. And then you have alignments, you can use your favorite approach to train the network. Or, this is very inefficient because you're going to have to pass through the entire training data twice. Once to find alignments, then the second to train the model. Or more likely, during SGD, for each training instance, you'll have a 2-pass procedure where in the first pass, you're going to find the alignment using the current model and then use that alignment in the backward pass. So this making sense, what we did over here. Okay. And so this is what we do, right? Now, that's a beautiful procedure. And if you have enough data, this almost always works. The caveat is, enough data, and it's also very heavily dependent on having a decent guess for the initial alignment. So it's prone to very poor local optimum. So instead of guessing an alignment, here's an alternate solution. Let's not commit to an alignment during any pass, but consider everything. And this is what we're going to see in the next case. how you can train without explicit alignment. The connectionist temporal classification paradigm. Actually, the model itself is CTC, but we're going to use the forward-backward algorithm. And we have also mentioned this problem with repeating symbols. So we're also going to be looking at how you can deal with repeating symbols in the next class. So I'll stop here. Any questions? If not, we will stop the recording.